cycles per second and generating acoustic energy within the reactor of about 3 watts per centimeter. We have a control of the gas pressure and the gas and the liquid temperature, which is we're circulating D2O through this reactor, and it's very important to keep the temperature and the pressure at the correct values so that the cavitation will occur. If the pressure is too great, then we dampen out the cavitation. If the temperature is too high, it'll just foam. So you have to be careful about that because we're putting quite a bit of heat in here. We have to put the liquid through a heat exchanger to remove the heat as it's made. The gases that were used were deuterium primarily, but sometimes we use argon and carbon mixture. We didn't find very much difference in using these gases. It doesn't seem to be a really important component, but there are some advantages that they're known. I think I'd like to put another graph on here. Now here we have an acoustic wave that's passing through the heavy water, and as it passes through the heavy water, the pressure decreases. We have a bubble that can be forming here, say at about 10 microns, and as the pressure begins to decrease, it starts growing in size, and it begins to taper off. It's growing in a fashion where it can gain mass in a rather slow fashion. This period here is from here there's 25 microseconds, which is long compared to the point when you get here where you start an adiabatic collapse. And this collapse appears when you begin to get a positive pressure built up in the acoustic field. And there is an acceleration and a boost to this bubble, and it accelerates continuously on down to a point where the energy in the bubble is increased a tremendous amount. If you look and you say R maximum is 100 microns, and R down at this point is 5 microns. We have this tremendous leverage. Now, if you're in a system that is called basically a stable cavitation system, the bubble will recover and gradually, through dampening, will oscillate back to its original shape, getting at its original size, and ready for the next oscillation or the next acoustic wave to pass through. And this bubble is an oscillating bubble, and often in recent few years, sonoluminescence has sort of come to the forefront, and this is basically a sonoluminescent type of system. Now, if you have a little bit more energy and the acoustic wave is a little bit deeper, what happens is this bubble cannot recover, and it goes into a catastrophic state, and with a jet formation on the surface, and this jet will take the entire contents of the bubble and inject these contents at very high temperatures and pressures into the lattice, which can cause some very interesting events to occur. And I would just like to explain that this kind of destructive cavitation is called transient cavitation, and the sonoluminescence type of cavitation is called a stable cavitation. What I would like to point out is the results that we got from this. We have a closed system. We have difficulty with the calorimetry, but I think it can be done in a satisfactory way using cooling curves which are characteristic of, we have several different components to the system, so we have to monitor each component as an individual. So we have thermocouples on all these components where we carefully look at the temperature, and then what we do prior to that, we need information on the system. So we turn all the power off. We have two pumps and we have the power supply putting energy in. And these cooling curves will define a profile of cooling characteristics of each component that we are using. Adding these all together, we can get an overall picture of what the total heat distribution is, and we can get also a balance, because we run this at a steady state condition, and we can run it for a number of hours. The temperature is generally around 50 degrees centigrade. We run these for as long as 3 days, and generally for 24 hours. I think what I would like to do now is just put on our results. This is such a complicated topic to discuss in a few minutes. I'm leaving out gigantic portions, but I think the results are probably as important as anything that we've done. I would like to put a graph on here that depicts one of the things that we do in a closed system is we find that we can find, if we take the gas that has been in the reactor and circulating with the D2O over a period of several days, we can take this gas and we do an analysis of it, and we see helium-4 as one of our products. We also see D2, we see HD and other kinds of products, but the helium is the one that we've been trying to measure. We started trying to measure helium-3, but we never could do anything satisfactorily with the helium-3, but we did find helium-4, and these samples were measured at a couple of different laboratories, and the amounts were quite large, so we don't have to worry about the natural abundance, I don't think, of the helium that's found in the air, because the magnitude was in the order of between 50 and 100 parts per million. And we're coming to a conclusion here. What I'd like to say is that we took the helium-4 in 4 of our analyses, and we took the watts that would be equivalent to the helium product, and we took the watts that we found as excess heat, and we made a plot, and very roughly it corresponds to about 20% accountability via the helium-4. We also found a very small amount of cadmium when we did an ICP mass spectroscopy of the dissolved sample. The helium-4, the cadmium-114 isotope that we saw was not very large. It was only 30 parts per million, and maybe it could account for 1% of the total heat. But I can't go into detail about that right now, but I'd like to close and say thank you, and if there's some questions, I'll try to do my best to answer them.
Thank you very much. Are there any discussion? Yes, please. And would you please either speak up very much or use the microphone presently?
Let me make a question. Which way you are speaking better? Stable calculation or determinant calculation?
Pardon me?
We use transient calculation.
Yes.
So you are pulsing or you are irradiating in sonification in CW or pulse which way?
I didn't get the question exactly.
Continuous wave or pulse?
Oh, I'm sorry. Yes, we use a continuous continuous energy input, continuous wave.
Continuous wave, plane wave.
I'll tell you, I can explain what we have. We have a commercial device that is a horn. It's made out of titanium. We put that in a water, circulating water. We have a stainless steel disc that we use to separate that from the reactor. We run this system at very high pressure to reduce cavitation damage to the stainless steel disc. This transfers the energy through the water into the D2O system. And we
Do you measure the acoustic intensity on that spot which you desire to have cavitation?
No, we don't measure the acoustic intensity in the system. We just use a single acoustic intensity.
So that means that you are still within something.
We do measure the acoustic intensity. We measure that by putting a heater of equivalent energy into the system and then run this as a blank. And then we look at the heat characteristics of an equivalent heater and look at the profiles of the system using the heater. We also run pure water systems and check with this also to see how the heat is being.
Well, heat doesn't itself define the acoustic intensity because the transducer itself heats for itself, and other component also heats for itself, and acoustic intensity is not, in that case, relevant to just a heat. You understand?
I guess I'm having trouble hearing.
And the heat itself doesn't define the acoustic intensity because the transducer itself gets heat, the wall itself gets heat.
Right. Everything gets heat. Actually, we're putting in something on the order of 300 watts.
What per which area?
Which area? Oh, okay. We put it in both the light water system and the heavy water system. There's a distribution between the two, and there's a coupling between the two. Now, what we measure is the total energy that's the input of all the total acoustic energy in the device, and we try to sort it out. But the heat loss from all the elements have to come together to give you a value for the excess energy.
Excuse me, I do have to interrupt this discussion now. I suggest we might want to.
Yeah, we can discuss this later.
Because there are a few more discussion remarks, and we have to go on to the next one. There was one question I didn't. Have you done this with platinum?
No, we have done it with stainless steel, no effect. We've done it with titanium with some interesting effects. We like to look at more metals, and we plan to do that.
Two last questions.
Color for your luminescence, and second part is, you say 3 watts per square centimeter. Is that at the face of the horn or on the face of the cathode, on the face of the metal?
Okay, well, now your first question, we're not working in the sonoluminescence area, so there, we've looked for sonoluminescence, but our temperatures are very high, and this is not a good environment for sonoluminescence.
And the answer to the second is we deliver 3 watts per square centimeter to the palladium target.
My question is the answer. One last question.
Yes, if you try this with light water as well as heavy water, you get the same production of bubbles in both waters.
Yes, we've tried light water and heavy water. The systems are a little bit different, but we don't get any excess energy in the light water system.
You get the same number of bubbles per intensity of the wave.
Well, we really don't count we can't count the number of bubbles, but the number of bubbles aren't really the critical factor. So I don't feel that you need to have exactly the same number of bubbles in both systems to get a fair measurement of what's going on.
But you do get bubbles in both.
Oh, of course, yes.
Thank you very much once again. entitled "The Method to Improve Algorithms Used to Detect Steady-State Excess Entropy" by M.R. Swartz from JFT Technologies.
First of all, coming from Boston, I'd like to thank Tom Castle for helping getting this meeting together. We're sort of starved out there. Second of all, this is a second archaeo-cold fusion discussion following the one before. And again, there's the advantage of hindsight, and I'd like to point that out. This began following an analysis of the MIT Plasma Fusion Center's Phase 2 experiments. Where is the controller for the... Nice job. 5 slides. Those that are interested in seeing the whole analysis of the Phase 2 data, there's a poster, and this is a portion of it. Also, if you're unable to follow part of this, you can go back and look at that. I'd like to point out that this application is applicable to all signal processing, and there's a lesson here. Now, first of all, the way the Plasma Fusion Center conducted their experiments, it was done as on an isothermal basis, where the putative experiment was such that if there was excess heat, to maintain a constant temperature, the heater power would thereby go down. Thereby, the attempt was to determine the excess heat on the basis of a regression fit, and we'll go into that now. The plan of the Plasma Fusion Center was to take that baseline shift and determine the anomalous heating on the expectation that this would be different from zero if in fact there was excess heat. I'm not going to really get into the curves. This is what I call a type 2 curve. If you go look at the poster, you'll see what it is. We're going to ignore this for now. What they did was shift it down, and we're going to talk about how they did it and perhaps a better way it could have been done. And the way that this was approached was to do a Gedanken experiment of using that algorithm on the case where one would create a hypothetical case where in fact there would be excess heat occurring at some time t. So for example, here are three Gedanken experiments where in the first case we were lucky enough to have a steady baseline, and at some time t in our putative experiment there's a turn on of some excess power, and therefore the heater power gets to decrease to maintain the same temperature. The second case that was examined was the case where the baseline has a slight drift, and the third case was the superposition of that baseline shift and then a step function where there would be a sudden turn on, which in fact has often been seen and reported from the initial experiments. Now, what we're going to talk about is the linear regression, and we have two types. I call them YHT and YHF, for true and false, and these are predicated upon whether the linear regression is based upon the initial curve prior to the occurrence of excess enthalpy. And we'll take the two cases. Let's take the case first where it's done right. In that case, we do a regression fit. Now here are the three cases. Here's the heater power curve, which has a constant baseline and then a slow turn on at time t. Here's where the general baseline shift is seen along with the turn on and then the step function. In each of these cases, a true linear regression fit is made, not to the entire experiment, but to the baseline. And in fact, when one turns it around and calculates the true excess power by taking the linear regression and subtracting the heater curve, one then is able to, in fact, in all cases, reconstruct the putative, in this case, hypothetical excess heat. So here you see the step function come out. Now, there's a bad way to do this, which is to fit the entire curve. And you'll see what the effect is. In fact, it'll end up masking the entire DC signal. Here, for example, we have this false linear regression fit, where the attempt is to fit the entire curve, and this is done in all three cases. And unfortunately, what happens is when you go to calculate the excess enthalpy, in each case it's masked, and this is the result. Now, in all of these cases, all DC signals are masked. In fact, the only remnant that remains is in the case of a step function, this little sign, which I call the reverse Z. It's not really anything to look for. This is the sign of a poorly designed paradigm. In fact, to get the reverse Z, you need two things. You need the bad paradigm, and you need a step function in the excess enthalpy. Two things occur by looking at this conductant experiment. One is, if you fit the entire curve this way, you can mask any DC signal. In fact, the only thing that would have survived would have been an AC excess enthalpy. As a corollary, if you work it out yourself, or if you go look at the poster, any attempt to use this algorithm will absolutely fail. Well, I mentioned the reverse Z. Again, this is not something you want to find. It's, in fact, I guess it's akin to looking at a wave on the surface of the ocean and trying to detect a fish underneath. It's not a very good way of doing things. But let's go back to this type 2 curve where we do a really good fit here. That's in red. What happens is when you look at their signal, you get this very mild reverse Z effect, which matches the hypothetical curve. Now, two hypotheses can come out of this. One is, what if we do the bad algorithm to some true cases where excess enthalpy occurs? And two, what if we go back and look at that experiment and do it right? And that's what this shows. Now, if you look at the poster, there's actually 3 ways that we went to calculate the excess enthalpy of that experiment, and all of them gave turn-ons at times equivalent to what Drs. Fleischman and Pons showed initially, and excess enthalpies very similar to what they also described. And here you can see, for example, when you do the correct fit to the beginning of the curve, in fact, their experiment appears to have been positive. In fact, at a level of approximately 63 milliwatts, which is pretty close to what was expected. One of the things we tried, I went back to Dr. Fleischman and Pons' initial experiments, and here you see the temperature and the excess power and energy. And I was curious if we could, in fact, now do the bad algorithm and see if we can get the reverse Z. Again, we would only see it because we have a step function, and we'd only see it in the case of the bad algorithm. And in fact, we do in all cases. Here's the case with the temperature. We see the reverse Z matching the hypothetical curve. We see it in the case of the excess energy, and in fact, we even see it on the log curve of the power. I think the important take-home lesson is it's something to avoid. And the fact is, if you try and fit the curves to the entire signal, you can wipe out the whole DC signal.
Thank you very much. Is there any discussion?
Let me just get it straight. Let me get it straight. You say if you fit a whole curve using non-linear regression or
It's a linear regression.
linear regression.
Correct.
Linear regression. You simply lock something into a constant curve somewhere or into the slope.
And erase it.
And you lock it into the slope and erase the
With that paradigm, they would have. In fact, no matter what signal would have been created, would have gone to 0.
Yeah, I know that has followed us a lot also, that you can eliminate signals quite easily by using a linear curve
correct. Unfortunately, in retrospect, in this case. There's no more discussion. Excess heat experiments on cold fusion to titanium values by Professor Zhang and his group. The talk will be given by Professor Zhang. Professor Zhang is from Chengdu University in China. Professor Zhang. He's not. Then we will proceed to the next paper.
I want to start by saying that I am basically doing this out of my garage. I am doing this on the lowest budget possible. I'm not a national lab. I don't have access to large chemical analysis and things like that. But what I do have is plenty of time, patience, and I've been at this for 4 years now, so this is sort of a combination of a lot of work over a long period of time. It may be a little sloppy by your standards, but I think that it will provide something. I wanted to say, emphasize the fact that I am doing this in a rather crude way. This was actually produced by my daughter here, but I'm basically using aquarium baths for my constant temperature. I control this with a photochemical type controlling system. It usually stays within about 0.2 degrees.
Focus.
Okay. My cells themselves are very small. I usually run somewhere between 2 to 30 milliliters. This is actually a 2 to 3 milliliter microchemistry type test tube. I have, in this case, a glass bead thermistor. I use thermocouples sometimes, thermistors later on. I'll tell you why I moved to thermistors a little bit later. I have a fairly heavy gauge platinum wire for my anode. The palladium is a heavy wire insulated at the top with connected to either nickel or platinum. This is a series of experiments. And my resistive element is a small platinum wire wrapped around that insulation so I can stack it in that small volume. For those that want to know, I have done runs where I take the thermistor and run it up and down to see that I don't have large picture gradients within the cell, because when you're that small, then you don't have much problem with where to stick the thermometer. Also, I have done platinum for my blanks and things like that. My uncertainty in my delta T, which I usually, most of these that I'll show you in a minute are based on temperature differences inside the cell and outside into the bath. But that's around 0.2 degrees. My calibrations usually run around 3 degrees C per watt, to give you an idea. 3.16 is what I really am after is a recipe or prescription or protocol that will help people get started. I've looked all over, and people don't really say what their best recipes are in one place, and I'm trying to do that because we've got a lot of nuclear people running around that don't know exactly where to get started. I use palladium that's either Aldrich or Engelhart. I'll actually slice these things and do things to them. Here's one that's been cold rolled. Over here is one that's attached to a platinum wire with Teflon, I believe, with insulation around it. This one is warped. I'll come back to that a little bit later. But finding a proper piece of palladium is very critical to the experiment. I physically take this and put it under a microscope, look for obvious defects, if it has leader lines, things like that, and do not want to use it. Another way that I select is by the bubble pattern. Mine are clear systems, and I've noticed that when I have very uniform bubble pattern, uniform grain, it seems to work, so I want to have some quantitative measure. I actually will put a piece of palladium that's been loaded past 0.7, past atmospheric. I will take it out, put it in the little rack, and this is a series of small test tubes, Durham test tubes, but the amount of volume up here is related to the outgassing. When I have, I can then go measure this. If I have a uniform bubble pattern, I have uniform volume or near it. When I have one region that is outgassing a lot, I will have a variation in the standard deviation of the bubble pattern. I've drawn in roughly the error bars. These are somewhere around 8% excess. When you have a small standard deviation in the bubble pattern, it seems to relate to more excess heat. When you have a large standard deviation, which means spots that are very bubbly and outgassing a lot, you do not get excess heat. So that's one way that I use in screening. Here is a piece of palladium that actually was cut from a piece of Engelhart. It was polished on one side, I'll tell you how I met, and the other side was just rough from the hacksaw blade. Notice that this has a greater radius of curvature. That means that it has larger volume expansion than the smooth side. And what I believe is happening is that is causing greater volume expansion, more outgassing, more defects down in the plate. So it seemed to be important to polish these things. I did a series of runs where I had two rough sides. I didn't get any excess heat. I didn't polish one side, didn't see anything. I polished the end and kept the top part rough, and I got something. Remember, my error bars are pretty sloppy. They're probably about 8%, so it spans like that. It's just out of the mud. But then when I polish the whole thing, I start seeing things. I polish by Black & Decker polish wheel, and then I take aluminum oxide, the kind that's used in chromatography, nice and fine. Then I polish it up. Then I finish it off on cotton with cerium oxide, the kind you use in optical grinding. The cerium may be important in some people's lives. Anyway, the cerium oxide, it makes a nice polish to it, is what I would say. Also, you have to initially load them at slow rates. I did a series, this is 30, 60, 120, etc., doubling it across. When I do the initial loading very slowly, I think that I can start seeing things. When I try to do the initial loading up to the beta phase very quickly, I don't see anything. What I believe is happening there is if you load too quickly, as you go to beta phase, it expands, it develops stress in there, excess volume, cracks, defects, and you're never able to load it high. So loading it slowly causes it to swell up internally slowly. You don't develop those stresses. Also, back on the rough, one point I should have mentioned on the roughness, your bulk loading is dependent on where it outgasses, because you have to, the net loading is how much you go in compared to how much is coming out. And that is limited by that region that's outgassing the most. So when you have a rough surface, you have areas where your overpotential is less than at the peak. So if you have valleys, you have less overpotential, and therefore that will be some of the limiting sites of your loading. At least that's what I believe. Also, the time of these additives. I tried to put in this as aluminum. These were done at 50 degrees C, etc. But I put in aluminum before the initial load, and I don't get much. If I do it after I'm in the beta phase, I do start seeing some effect by adding aluminum. I think aluminum is fortuitous in that it has a low solubility in these kind of solutions, and therefore it's putting on there very slowly, so it sort of delays the onset of it. But what I think is happening on adding the things like aluminum is you're wanting to increase the fugacity, if I can use that term, inside the lattice. If you have cracks and crevices and you increase it too soon, those will just creep and they'll just grow because you have high pressures in those crack regions. If you load slowly, you'll have some healing because of that expansion of the beta phase, and some of those cracks and crevices, I believe, are healed as you do that initial loading. And then you do the additives, which will increase the pressures internally. Also, the anode configuration seems to be important. At one time, I was very cheap, and I tried to get by with just 1 or 3 or so turns of platinum wire as my anode. It didn't work. You got to have several. Again, you're limited by that area that you're pushing, where you're pushing into the lattice. The minimum electric field or overpotential or whatever the electric field at the surface is going to be where it's going to outgas the most, and that's your limiting area. Also on these anodes, I've heard several people mentioning the nickel. I've had some limited use of nickel anodes. If you do that, you probably should oxidize the nickel before you start heat corrosion down with a little trickery in it. I learned that from the Whitewater nickel stuff, which is a whole other story. But at any rate, the anode configuration is important. I usually use anodes that have been cleaned by going against some dummy material, hoping to blow out any active species. Now that you've got a piece, you've loaded it, you've got a nice surface that doesn't have lots of pits and voids and all that, and you've loaded it up to 0.65 or 0.7. The way I measure that is I just stop the current a little bit to see if it outgasses, and I know that I'm on the other side of the atmosphere, and I do that visually because that's the only way I've got. I'm trying to go to higher temperatures. This is a cell with a small condensing unit, small newer flask there. This was the start of things. But basically, I tried the cells previously and just increase the temperature of the bath. Start with the same cell and increase the temperature of the bath and monitor the excess power related to delta T. When you get up to around 80 degrees or so, you start getting boiling off because you're having delta T's of 10 to 20 degrees or so. So of course you're going to start boiling off when you put it in there. But it did appear that I had a general trend upward. These are straight lines just simply because that's all my computer plots. I got a cheap program. But at any rate, it did seem like it's upward as I went to higher temperatures. The problem is I can't afford a lot of heavy water because it just boils off. So I went to a refluxing system. Hopefully you can see this. This isn't the scale, but I have a cell down here. This is now probably around 150 milliliters or so. These black dots represent locations of thermocouples. Actually, one is a thermistor there and here and up there. But most of them are thermocouples. I have a central column. This is actually 40 centimeters from there up to this glass wool plug. I then pack some aluminum oxide for surface condensation sites, increase the bubble plates for the engineer types. And then above that, I have a recombining material. I have another plug there. There's actually a Tygon tubing that goes up and around to kind of prevent the hydrogen from going up or the heat just chimney out. Around that center column, I have a flow of water. And what I am doing is flow calorimetry over this condensing unit. So I have this well insulated. This part out here is the polyethylene foam that you use for water pipes and all, wrapped with glass wool. I flow in here. I'll tell you more about this in just a minute. But I flow in here and out here. I set my water bath at roughly 40 degrees. I try to keep my delta T at 20 so that the output is around 60 degrees. So I change my flow rate to keep a constant delta T. That's just mechanically done. I can monitor the delta T and that sort of stuff too, but I usually set it in there. And what this does is the bottom portion of this is around 60 degrees. Anybody trying this, there's two subtle things you need to be aware of that I need to point out. Number one, this does not come down on axis. It's off axis because you're returning cold liquids that are devoid of your electrolyte. It's distilled water. So if you come right down on your cathode, it messes it up. It cools it off. It stops your electron. That took me a long time to figure out. But anyway, you want to return that off axis. The other thing is that I want this section down here 60, 70, something like that. I don't want about 30 degrees. So I'm trying to keep this at a reasonably warm temperature and come down. Those side pieces, well, maybe I should back up a second. These areas right there are actually widened pieces that I've packed with copper, that I put the thermocouples in there. I actually use a mercury thermometer. I believe mercury thermometers. But at any rate, thermistors and thermocouples are really bad. Thermocouples are bad at RF. I pack this. The idea is that when the water flows through there, I am averaging out over a larger volume, and I don't have to worry about the laminar effects on the calorimetry. That was advised by Hayden Burgess and said, what's those laminar flows? Here is my setup. Dewar flats down there, insulation. I pulled some of that away. I've got Boraxo and lead bricks, so I don't have to wear radiation badges. Or that's actually to protect the dog next door, so he didn't lose all the house. But at any rate, I've got this reflux column here, and this is actually the tube that goes up to it. Over here, some other type of typical calorimetry type of. But this is a system. You can tell this is just in a garage. I've made my own wood devices or whatever. So it is somewhat limited. So that's what I really wanted to show you. I'm now going to venture, I'm switching gears now. I want to venture into some areas that I may or may not should, but I'll tell you just a minute. That's not the right one. That is, I have found some peculiar effects when I use magnetic fields. I'll actually take this electromagnet, put it down in my aquarium and run these things with delta T. And I see changes that I don't understand. And I only say this in that this is a non-destructive thing to your cell. And if you have a cell that's running 20 or 30%, you may want to put a magnetic field across it and see what happens. It's surprising. Now, I have not done the calculation. I made the heat losses and all that, and the calibration is a pit when you have these large chunks of metal out here. But you may want to try that, is my only point, because it's one of those things that's fun in life. I also put an RF field around there and tried some of that. The jury's out on that. I don't know what is happening, but the heat goes bananas on it. And if you try this, it's should be around 82 megahertz, just for those who want a particular frequency. It's frequency dependent. And lastly, just because we're before the luau, and since Roki in the first conference showed his hopeful cold fusion car, I wanted to show you what I believe is the world's first, that's RF now, right? The world's first cold fusion rocket. I've taken water, this is for all in good fun. I've taken a water rocket, I've put a fuel, cold fusion cell in it. It's hard to see here, I have to take this off a video. I've loaded this up, I've put in 10 watts for 20 minutes through resistively. It heats up to 95 degrees. You pull the plug and it just sits there because there's no pressure in it. I've done it with light water. It goes up about 15 centimeters because of the hydrogen oxygen pressure. But when you put the heavy water in there, you get that extra 30%, which is just enough to boil because I picked the right loading, which causes steam pressure and it gets up about 30 centimeters. You rocket scientists. This is also aimed at the neighbor's dog. But the thing is that this is, you rocket scientists, the problem is my mass fraction is terrible because I have all this weight of plate and platinum, etc. But the reason why I did this is for those of you that have been fighting the patent office and all that, they say it doesn't have any use or whatever. My point is, I don't care if it's an energy system or if I have to wind it up for 10 years and then release that energy in 10 seconds. I have a useful device that at least gets off the ground. So,
Yeah.
Dennis, could you tell me the approximate ratio of the cost of your total experimental program to the tokamak program over the last 4 years, 5 years, and also the other ratio that I'd be interested in is the ratio of the cost of the DOE ERAB report to your work.
I don't know how much they're spending. I'm spending maybe $4,000 or $5,000, something like that, over 4 years. Okay, most of that has been in palladium. I didn't mention it, but rhodium costs a lot. I've tried the rhodium, rhenium alloys, all that kind of stuff. Those are interesting. That's another way to avoid. Yes.
That was a very good line to stop on. We are running late. We are running late.
The cracking. Okay, because you're already in the beta phase. I think that occurs as you're expanding out.
Please conduct any additional discussion on the see you at the luau. This terminates the session.
Aloha.
Many people believe that experimental error is going on. I don't, for the sake of this talk, I'm going to continue down. Nuclear reactions are more or less what's left in terms of nuclear reactions, a question of what type of nuclear reactions. Many theorists in the field, in fact, most of the theorists in the field are working on fusion reactions. I'm going to bypass fusion reactions. I'm going to bypass fission reactions, bypass electron capture decay, and get down to the bottom to things which are new. I've spoken about neutron transfer reactions at previous meetings. I've not talked about lattice induced reactions. Both of these constitute the bulk of my ideas and theories these days. The place to start the argument has to do with energy exchange between nuclei and lattice. The place where energy exchange between nuclei and lattice shows up in other fields is Moscow effect. Moscow effect, you might have it's like a nucleus emitting a gamma, and in doing so, there might be lattice recoil. In the case where the lattice picks up the recoil, you might have a zero photon transition. So, for example, you might get a Mossbauer pit superimposed on top of one to a multi-photon interactions for the light shape. It turns out the basic physics effect that we spend most of our time is actually hiding here inside the Mossbauer pit. The Mossbauer pit is the line shape of the Mossbauer pit is a combination of Lorentzian and Gaussian. Lorentzian is not going to do a whole lot interesting for you. The one and two multi-photon processes come down from kinetic effects. I don't think kinetic effects are going to do a lot for you in this problem either. So about the only thing that's left is the Gaussian internal line shape of the Mossbauer pit, which is previously not been really well explored. That Mossbauer pit has an associated energy transfer neighborhood of 10 to the minus 8 to 10 to the minus 9. So if I'm going to get that tough to deal with MEV, I'm going to have to be making a mountain out of it all time. I have analyzed the case. What happens if a neutron comes in and a gamma comes out? In this case, we have neutron capture, gamma is emitted. In principle, the initial momentum and the final momentum is matched. But I have a zero recoil of gamma and Mossbauer pit showing up. I would give a line, and I've analyzed the line shape of the line for neutron capture. What I find is there's a Lorentzian portion, there's a Gaussian portion. In this case, the Gaussian portion is under 5 million EV. We're getting closer to 10 EV. We still have a long ways to go. And we're going to be associated shift. Even in the case of Mossbauer, it can be shift or if you analyze this problem, basically what you find is that whenever you consider a transition in the presence of a lattice, when you calculate your transitions, your dynamics, you've got to include not only the nuclei, but you have to include the lattice as well. And so my theory today, which I'm presenting, is going to be the results of including lattice as well as nucleus matrix on the various processes. Okay. So consequently, if you want to describe lattice coordinates as well as nuclear coordinates, we take matrix elements which involve lattice-centered mass coordinates. Typically, when you do the calculations, you do it in terms of photon mode, amplitudes, and coordinates. As it turns out, since the lattice is different before and after, you need to take that into account. The way that I take into account is something called the Dushinsky operator, which I borrowed from chemical theory of polyatomic spectra. This is also known as Fred Condon factors, Long-Reese factors, and various factors in other areas of physics. The basic claim is that this operator and these factors can give rise to energy transfer in the case of things that we'll be discussing today. I calculated, I think I can dispense with this. I calculated line shifts and widths. This plot has a nice picture of the phonon modes for palladium deuteride. Palladium deuteride phonon modes include acoustical branch and optical branch. This branch corresponds to deuterium moving. This branch corresponds to the palladium motion. In the limit, you would replace one deuteron in the lattice by hydrogen. You change the lattice, consequently the photon mode frequencies change, and if the phonons modes have phonons in them, the phonon frequency shifts gives rise to shifts in the line position. And that's what I've calculated. We're up to 10 million EV, and that's about as far as thermal effects can take it. The question is, what do non-thermal effects do? And I analyzed the effects of having high levels of excitation in different phonon modes and calculating what happens when you transfer from initial lattice to final lattice. And most of the time, nothing happens, and I've analyzed that nothing in detail. You get shifts and widths on the orders of 10 million electron volts. And so at the moment, so far in the discussion, it looks like there's not really a whole lot of prospects for large energy exchange between the lattice. This is a problem that bothered me for quite a few months. It dawned on me that there was a solution to it, and the solution was to deal with basic ideas in impurity mode can jump a band gap. For example, if you had lithium-6 in the lattice and lithium-7 in the lattice in small quantities, it would make impurity modes. If lithium-6 accepted a neutron, it would make lithium-7, and in doing so, it would create 3 phonon modes from this impurity band to this impurity band. If the phonon modes are highly excited, then the energy exchange, the phonon modes take their phonons with them, and the energy exchange can be substantial. The basic picture that goes along with this is this kind of picture. And in the thermal lattice, for neutron capture, there might be emission centered around the resonant frequency. But if you have a gap jumping mode that's highly excited, you can move the line, and you can move the line a large amount in principle. You can move it by the number of phonons that are in your gap jumping mode times the amount the phonon mode jumps the gap. Recently, I guess it's dawned on me that possibly the most important modes in playing the Dirac problem, or really interesting gap jumping modes, are going to be modes in which deuterium gets displaced. What happens is the Dirac modes, in the presence of a Palladium vacancy, get shifted to lower frequency. So this is the kind of gap jumping mode, one of the kinds of gap jumping mode I'm going to have in mind. There are, of course, many others. If you go from 8 octahedron palladium-6 to palladium vacancy to 7, you'll jump down. You'll have another gap jumping mode for deuterium removal. So this constitutes a mechanism for energy exchange between nuclei and the lattice. I presented this at the International Moscow Conference, and it went over rather well. Now what I want to do is to take some of these ideas and begin applying it to cold fusion effects and phenomena. And the first experiment I'd like to address is the Kucherov experiment. In fact, probably it's going to be the experiment against those phenomena. Actually, if my friend is calling me forward, Kucherov's going to get up and begin a presentation. He's going to say, "No, you don't have to." But the basic idea, and Kucherov's presented, is about tomorrow's presented, and Cartwright's presented. We have a glowing discharge. Inside the glowing discharge, we have 5 to 10 torr deuterium gas, and we have a discharge. The discharge arcs, and John tells me, and so that's what told me that the sign of the arcing spikes in voltage and current, a high level discharge is a good thing. And what I found is I said, well, let me take that notion and not be, if you like, continue on as if they're fantasizing about what that might lead to. In order to excite your gap jumping modes, if you have a laser tuned at the right frequency, perhaps you can excite the phonon modes. Fortunately, there's 10 to the 20th modes, and the frequency selectivity of a laser is good, but it's not that good. You need spatial selectivity, and current should couple to the modes. The modes which are the gap jumping modes tend to be the most uniform in space. So the way that I would couple to it if I could is I would drive a current through the lattice and I would modulate it with the frequency associated with the phonon modes. During the arc and spark, you're probably generating the neighborhood of local disabling where arc and spark have discharges. Numbers in the neighborhood of 10 to the 50, 10 to 6 amps per square centimeter for a short time. The plasma, if it ionizes, has associated plasma frequency which will modulate the current flowing through. It turns out that if you start up with T pressure in the neighborhood of where these experiments are running, there's a plasma frequency that corresponds right near the gap of the palladium Dirac density system. This is the density photon modes sideways. If you're at 5 or 6 torr, you're right at the edge of where the palladium nodes are. So if you have an arc and you have an appropriate plasma that's ionized, you're going to drive these gap jumping modes, and you can be putting a lot of phonons in them. So let me go ahead and imagine that that's going to happen. Calculate as a Fermi hypertonic interactions. Probably early next year is going to be a computation of the estimates of the calculating the currents and so forth for this problem. If this works this way, the question is what are the ramifications? Well, if you can put energy during a nuclear reaction, then you can pencil drive reactions which wouldn't be driven otherwise. One kind of reaction is a it's oftentimes discussed in terms of an FT product, which is a description straight for the matrix element. And most matrix elements come out to have a lot of FT, and they were 5.5 to 5.7 in the range of palladium and related nuclei. In the case of lattice-induced beta decay, which is the first anomalous lattice-induced reaction I'm going to talk about, we will take the standard beta decay formula and you include the lattice. And you've got two things going. You've got these gap-jumping modes, plus you've got a recoil. If it's going to happen, you've got to be able to dislodge a palladium nucleus. And if you can dislodge or change the location of the palladium nucleus, you can take recoil of the electrons and neutrinos, and it can get the energy exchange to go. So I'm evaluating these matrix elements, and in the limit, if you do this, you get in terms of according to recoil, and you get the lattice energy exchange. So the first thing to show up, if you calculate all the possible beta decays, lattice-induced beta decays, the first thing to show up is decay of palladium, a backwards decay of palladium 105 to rhodium 105. If this would actually occur, you make ground states, you have activation of your cathode of rhodium 105 for 35 hours. If you have a little bit more energy, you can produce the first excited state of rhodium at 129.6 kilovolts. When we started our experiments, I said, well, you should look for 129 kilovolts, and you should look for 149 kilovolts. So we've been trying to replicate with the support of Pete and Enrico, the Kucherov experiment at MIT. I know that in Kucherov's data, this line right here is 129 kilovolts. I know that he presented on Monday afternoon the observation 129 kilovolt in a discharge experiment. He thought it was 130 kilovolt using sodium iodide detector. At MIT, we've been trying to replicate Kucherov's experiment with Kucherov's cell. The next approximation hasn't seen anything. One of the things that we saw, which has given us encouragement to keep going, was a feature which we got interested in. It occurs at 129 kilovolts to within enough precision to be a candidate for being this line. This is motivation to have you more interested in the theoretical arguments of ICCF-4 that we give shortly. This is not enough to prove a point, but it is enough to keep you working and continue to take data. So if this is right, you go from palladium 105 to rhodium 105. Rhodium 105, the energy levels from lead and Shelley look like this. The first two levels are 129 and 149 kilovolts. Jan says that he's got lifetime data that agree with this 40-second lifetime. So we calculate, use our formulas to calculate the lattice-induced beta decay rates. In this case, it's electron capture. The numbers look like this. Assuming you've got an arc and you've got a whole excited lattice. On the axis here is lattice energy transfer. If you believe that there's no effects of the deuterium on the vacancy energy, you only need 4 volts or so to dislodge a palladium nucleus. According to Fukine, stuff by MIT, did some experiments in this area. He said, well, in fully loaded palladium deuteride, you can actually have vacancies move at energies closer to 1 electron volt to the system of the vacancy diffusion data that we've taken. Along those lines, you get reaction rates which are absolutely enormous and can give you, in this case, activation of palladium to rhodium 105. The numbers for 129 kilovolt look like this. If you do produce 129 kilovolts in this theory, you will have to transfer at least 750 kilovolts, likely MEV from the lattice. 149 kilovolt excitation spectrum looks very much the same. I think this is, I don't have any interaction matrix levels between 129 and 149. 149 is weaker than you're going to get 129 showing up pressure, lattice energy transfer. energy will do. The next electron, or the next rate of decay process that will happen energetically by this transfer mechanism would be taking palladium-110 and going to silver-110. The energy level structure here, which is probably too small for any of you to see, includes a level very near by the ground state and then excited state levels. The second excited state has a lifetime of, I think, 252 days. And so you can get well in activation this state. This is the calculation for lattice-induced beta decay. In this case, you get an energetic beta. Now, you need to exchange about an MeV with the lattice to get this to go. In order to get the long-lived isotope, the long-lived isotope itself probably has a very weak matrix on it for coupling. I've estimated the rates to be down here. If you go to more highly excited ones, you can get a little bit more activation. The next one's 118. Now the yield fraction 117 and 118. I suspect it's not very large. A little bit stronger excitation of 118. If I keep on going, in principle, I could spend the next 45 minutes presenting plot after plot after plot of these beta decay rates. Let me simply summarize by doing all of them for palladium and putting them all on one graph. And basically, they look like this. If you transfer, if you get high excitation, you transfer several MeV, you would expect the production of C equals plus and minus 1 isotopes from this process around palladium. And rates, once again, are very much large enough to support the notion of having excitation during the following arcs in the Kucherov experiment. Let me continue on. If you can have beta decay, at some point you might introduce positrons. Positrons start showing up in this theory also at quite a high rate at 2 MeV or higher. This corresponds qualitatively to the description that Carl Lee wrote about when it turns the current up, it usually just gets down, and after sometimes see some annihilation lines showing up. The positrons are very interesting, very distinctive. We keep on going. The question would arise as to if there's any way to take advantage of this to induce a decay movement by C in order to prove whether this is either going on or not. And so I'm proposing now an experiment that could in principle be done that I think might settle the matter one way or another as to whether it works this way. If you had palladium-107, and or you get palladium-107, if you found a way to get some palladium-107 and put it into the lattice, palladium-107 decays to silver-107, and it's a relatively slow decay, 6.5 million years. If you look at silver-107, the palladium decay all goes to, because of energy, all goes to the ground state of silver-107. If the lattice could exchange energy in this process, it could both increase the rates, plus it would open up the 93 kilovolt channel. I've calculated the rates associated with that. The answers look like this. Rhodium, the decay to the ground state of, this is rhodium-107, so this is silver-107, this label. Silver-107 ground state would enhance by lattice energy transfer, but the 93 kilovolts, which would give rise to gamma that you could see, would be enabled right around 100 kilovolts. Given that all the energy transfers associated with heat production, tritium production, everything else in this model occurred about at above 100 kilovolts, the occurrence of 93 kilovolt gamma by palladium-107 doped cathodes would be a signature, I think an unmistakable signature of the prediction of sort of a proof that energy exchange with the lattice is going on in this fashion. Let's keep on going. Jan says that he sees alphas coming out. So let's look into a possibility for lattice inducing alpha decay. Normally alpha decay would use gamma theory. It looks something like this. In the limit that you have lattice induced you have to do this non-perturbatively to get a good answer. If you keep on going, if you were to add more energy, you could begin to see proton decay. It has occurred about 8 MeV. John's been talking about potentially observing fission products. And first time he told me that, I thought, okay, he's experimentalist. 3 MeV cool here to prevent fission decay is something that is really hard for theorists to grapple with. Yet I'm finding out that following John's suggestion, I'm at the conference discussing exactly what it is that he's proposed. By looking at what I took first, the fission energies for the various, the excess energies for the various fission decays look like this. And then, for example, vanadium decay would be here, titanium, chromium decay, which would be the biggest, would be here. You do get a fair amount of energy out from having done this, and this lattice-induced excitation could in principle do this. The graph for 104 looks almost identical, and if you plot out the rest of them, they're basically all pretty much the same. You can calculate the fission decay rates for various branches and pathways. And what you find is that in order to get, for example, a nearly 50-50 split of titanium, which is one of the most energetic, and for its C, when the first one to turn on, you need about 40 MeV of lattice transfer. If you think about that, you say, well, that's a large amount. But when you think if you can excite the photon modes to 2 or 3 MeV, factor 10 away to 20, 30 MeV is only a factor of 10, and since the excitation is coming from external current, it seems to me that it's not that outrageous and outlandish to take the next step to go there. So at this point, I would have to say that Jan's, as colleagues' ideas and approach to observations, could in principle be explained by something like this. Let's keep on going. If you try to disintegrate a deuteron, if you have no gammas to do it, you would calculate the rate from the cross-section times the intensity of gammas that you have. It turns out that if you can transfer energy from the lattice, that the local DC fields and B fields look like gammas, especially if energy is transferred in. Consequently, you can get deuteron disintegration, and the formula, including the lattice at the end of the day, would look something like this, where the virtual intensity would come from the local E field. The E field would come from S equals MA acceleration, and estimates for the various rates look like this. If we plug in numbers, we get things that look like this, and we get neutrons out. And the neutrons are going to be 2 MeV peak if you can transfer that much energy. If you transfer more energy, you get this higher energy tail that falls down, very much like what the Roots group discussed. These virtual photons can also scatter. It's very analogous to what happens in channeling radiation problems. The scattering cross-section nuclear Compton scattering works this way. If you scatter these virtual photons exothermically, well, once again you take into account F equals MA to get your related to your acceleration. And you get kinetic factors that give you a continuum that looks like this. The deuterons scatter first. I've chosen whatever you for energy for inelastic free flow. That energy would look a bit higher. It would correspond rather well to the Luch continuum diagram. I might even make it. Okay, so that's lattice-induced reactions. The question is and that's supporting evidence for why I think that you can transfer energy, you might be able to transfer energy between nuclei and lattice. I've been discussing neutron transfer reactions, where you get a neutron from a bound state up into continuum states, and then you capture it to a distant bound state. That's as a way to get gamma and alpha incoherently. And heat production in this theory would occur by having the first several months, or in the past year or so, I've actually get a rather rigorous quantum field theory model for this process. Having sat in the back and knowing how small this screen is, I don't expect that anybody past the sees about 10 feet in front of me can actually see this. But if anybody cares, of course, I'm willing to show it to you and talk at very great length about it. It turns out that this model that I've written down is very much like models that are used in condensed matter physics. In fact, the model itself is essentially identical to something called the Anderson model in condensed matter physics. My students made up this view graph and said, well, here's the basic model for what we're doing. You've got bound states, you've got continuum states of neutrons, and the coupling between the two is first order. It works like this. And this is just like a similar case for electrons in the lattice. You have bound states, you have continuum states, and you have coupling that looks like this. My student noticed that there's this correlation term, configuration interaction term that shows up in the electron code. He says doesn't show up here. And after thinking about it, this corresponds to having 2 electrons at a site. If you have 2 neutrons at a site, if you have 1 neutron to a proton, you get a deuteron. If you have a second, you get a tritium. So strictly speaking, this term shows up here, and I can go back and talk to my student about it and convince him that the analogy is actually rather precise, or more complete than he had thought. A difference occurs between the Anderson model for electrons and the model I'm talking about for neutrons. Instead of electrons hopping, neutrons are now hopping. The lattice is involved in a greater degree in the model I proposed. In the Anderson model, usually lattice exchange of photons is not included in the analysis. The absence of not including this in this column will lead to completely incorrect answers. You can use standard techniques that's used on the Anderson model to analyze this model. You can calculate hopping. You get hopping rates which are very interesting. You could do it using something called either Markov rotations or Wolf rotations. You get an effective mass for hopping, and this is very interesting. I developed something called a 1 neutron approximation for this. And I think what I'm going to do is skip a lot of the math associated with it. But I can get an expression for reaction with non-local neutrons, which corresponds to heat production, tritium production. And the numbers that I get out are very interesting. If I look at the energy levels to see what could hop from what in order to get the heat, what I find out is that palladium 105 donating and lithium 6 accepting to make lithium 7 is 156 kilovolts. That's the very first one that shows up for excess heat with low energy transfer. Palladium 106 donating and palladium 104 accepting is the second one that shows up. If I focus in on this, the palladium to lithium looks like this, and it would necessarily follow from discussion of root experiments. Associated rates for this process, as I said, looks like it will be bigger, considerably bigger than the rates for the inelastic process. And I'd like to conclude by putting up a slide which summarizes all that I've said during the last 40 minutes. The slide's pretty busy, but there's 2 axes on it. One axis is energy transfer from the lattice. And if we go in this direction, we talked about activation of palladium, beta emission, gamma emission, positron emission, alpha decay. And if I were to go further on here, I would get lattice-induced fissions. If I go in the other direction, the reactions give energy to the lattice. I pick up palladium lithium first. So this would be heat producer. I get palladium, again, this would be heat producer. The higher I go strong afterward. So, for example, Hans inflection would be working up here because the higher you go in this direction, this axis is density of delocalized virtual neutrons. The higher you go up, the more power you get. Lower here, you have kilowatts per cubic centimeter. I haven't marked it in here, but there's tritium production one I'm showing up here, a little bit over 500 kilovolts. I notice my lights on red, which coincides roughly with my finishing my talk. So, questions?
Your question.
It's punctual call. I'm just in time. Yes. Yeah, time for questions.
I have three questions, but I will be selective. First thing is, I think you're pushing analogy with Anderson model too high, because in the Anderson model, electron hopping involved in electron model, whereas in the model of neutron transfer, you really need 10 MeV energy to do it. And that's my first question. Another question is, how do you suggest any one particular case where you can really do the experimental test of your idea? Definitely, you mentioned so many things, but let's pick up just one and tell me how you want to test this.
In answer to the first question, the analogy with the Anderson model comes about simply because the equations that I get when I write down my model, if I look at them mathematically, they're identical to the modified periodic Anderson model. And that's the beginning of it. He asked about the techniques you can use to analyze the modified periodic Anderson model you can use on this model, such that you can get expressions that are identical. I have found that the expressions for hopping, for mobility, and so forth that I get by plugging in the neutron masses and the associated MeV levels of energies gives me highly non-trivial and very interesting predictions for hopping rates and so forth. In terms of predictions of what you could do to verify this model and test it, there's of course a very large number of predictions. For example, if you put in palladium-107 as a contaminant and you saw the 93 kilovolt amount, I think that would be very, very strong evidence. If you saw enhancements of palladium-105 associated with heat, that would be very strong evidence in support of the palladium mode. If you saw transfers to lithium, if you saw change in lithium isotope ratio, that would also be very strong evidence. If you could see characteristic activation of palladium, that would be also very, very strong evidence in support of this. And it turns out that the theory also looks much more consistent with light water experiments these days than it did before.
What degree of periodic, I have two questions. It's obvious you're assuming periodic order to a degree in what you're doing. And the first question would be, what degree of periodic order is assumed? In other words, does it go down to the nuclear scale? Or?
It's, in principle, it's not supposed to be an assumption. If you calculate out the Anderson model for this, you get explicitly the constraints on periodicity. Yeah. At the moment, that's still research in progress.
Yeah, because well, the curious thing, it gets back to a degree of what Dr. Kim said. I think it could have rather important implications associated with the energy scales and so on. The second question is the importance of magnetism. Are there implications associated with magnetism in various transitions?
At the moment, the heat production, tritium production, and so forth, in this version of the theory wouldn't be affected by magnetism. But on the other hand, if you put on a magnetic field, that should do very interesting things for disintegration lattice-induced disintegration of deuterium and neutron production. Additionally, continuum gamma production should be affected by strong magnetic field and dispersion theory. So that would be another test one could do.
Yeah, well, I throw that out to you as something interesting to consider, especially in light of what John Bacchus said and in light of what Lex and Ravens have seen. Thank you.
Well, I have lots of questions like the Mossberg effect being 10 to the 6 slower than reaction rates from nitrogen transfer. What I'd like to concentrate is boundary transition problems. I mean, what you're essentially saying is that inside a lattice, certain things happen, but the problem is outside the lattice in the rest of the world, you have different things, you have penetration problems, which reduce the diffusion rate. You have branching ratios, where by charge symmetry you equal numbers of tritium and neutron, and where the helium-4 is down by a factor of 10 million. Now, could you talk about where this transition comes between the rest of the world and the lattice, and in particular, what kind of lattice? I mean, if you take water, if it's ice, is that a lattice? Would you expect cold fusion ice, or would you expect cold fusion water? So could you apply the problem of boundary conditions and transition, and the particular problem of water as liquid and water as ice?
You asked quite a number of things, and I'll do my best to respond to them. I guess to summarize, what I'm saying is that when you calculate your nuclear rates, I'm making the strong statement that you ought to include the effects of the lattice and matrix elements. Previously, I don't think that so much attention has been paid to that. And if you do that, then what I'm saying is that under fairly well-specified conditions, there exists the possibility for large exchange of energy between the lattice and the nucleus. Water, I have not analyzed, but I would imagine that the first question I would ask is, would you get a band gap for the photon modes? Because the kind of physics that I've been talking about requires high excitation of band gap jumping modes. If water doesn't support a band gap, then I think we stop the story. The second thing is water is not the world's best electronic conductor, and then the non-electron conduction activation and purity modes is my preferred mechanism for doing that. So I'd be more interested in metals than in water.
Okay. There's no other question? Okay. This is the last one.
Would it help you to know that one can infer from some experiments in Stuttgart by Kirchheim that there is a very strong attractive interaction between vacancy, palladium, and deuterium? Would that be helpful to your theory?
I think right now I'm leaning towards that as being the most interesting area for my anomalous energy coupling between nuclei and lattice.
A number has not been inferred quantitatively for that interaction, but it is clear that there's a very strong interaction, probably of the order of 100 kilojoules per mole between dissolved deuterium and the vacancy.
Okay. Is there anything we...
Switch yours. Yeah.
Okay. Let me begin this talk with a warning. And this is a warning. And first, hoping, of course, that the Surgeon General is going to legalize quantum field theory also. Okay. Then this is just the important preface to this talk of mine, which will go through this text. Maybe I won't go this course that will not go there, will not be won't have time. Just discuss first the problem framework, second the PGD system, and then the problems of cold fusion, and finally. So as for the problem framework detection, I will concentrate mainly, actually only, on the flash pump system, namely PDD system at high loading. The problems that we have to solve are two kinds, alpha and beta are the two kinds. First, alpha is the quantum electrodynamics of the Ds that enter the PD lattice, which can be formulated in the form of questions. Alpha 1, why does, in the gas phase, D2 at the surface just splits to DD and then go to the lattice? And in fact, why does, and there's an ample evidence for it, D plus and D minus have two dependent dynamics in the lattice, so that D plus stays in the direction form. Of course, with some screen, that's besides the point. Alpha 3 is why is D plus or mobile in the lattice of RH. Alpha 4, what are the phases of the PDD system? And I think Martin tomorrow will give some better description at this point. And alpha 5 is what happens during electrochemical loading, which is a big mystery, of course, from the theoretical standpoint. It's not a mystery anymore, from the experimental standpoint. And why does one observe heat after death? This very interesting talk, which 10 points yesterday, or the other one, the day before yesterday. The second set of questions, problems, is the mechanism of cold fusion that I did with the PDD system, which can be reformulated in terms of questions. Some questions, beta 1, how can one overcome the Coulomb barrier? Which is the main D diffusion dynamics? Can we understand rare processes involving neutron, tritium, X-rays, activation? And after beta also we have gamma, and the gamma is the theoretical framework which has been used in this talk. This is the QED coherence in condensed matter, which is just trying to understand what QED does in a complex system, in a highly dense system like we have in a complex system, condensed matter. I'm writing a book, which will be soon finished, but there are lots of references, lots of lectures. One of this is this one. And this program, this research program, which fully recognizes the role of the QED electrodynamical interaction in matter, whereas the general set of picture condensed matter, including the Anderson model of high waves of Peter, only considers electrostatic forces among the constituents, the basic constituent matters, like atoms, nuclei, and so on. Now, according to this picture, which fully recognizes the role of the electrodynamic interaction, then matter can be looked at as a set of plasmas. And the plasmas, let me remind you what the plasma is ensembles of identical charges oscillating around the equilibrium position with a typical frequency, the plasma frequency, which is of the order of the ideal plasma frequency, which is related to the charge of the system, the inverse proportion to the root of the mass of the system, and the electric proportion to the root of the density. So, the plasmas which are relevant, I believe, in the Fleischmann-Pons system are the d-electron plasmas of the palladium. These are shells around the nucleus of palladium. This is just typical phase of the phase center lattice. They can also, these shells, they can oscillate in phase in any direction with an amplitude which can be approximately calculated, maximum amplitude, rather large, of the order of atom and angstrom. And the very large plasma frequency of the order of 100 electron volts. The other important plasma of the system is the S electron plasma of the electrons that invade the lattice when the Ds goes there in order to neutralize the system, and they occupy, of course, the positions which are left out by the lastly, but of course not leastly, is the D plus plasmas, which are essentially of two types. One of the Ds occupy the octahedral positions, and in this case, to minimize the energy, the oscillation will be in this direction, or when they occupy the regions in between the two tetrahedral positions, and this shall be called the tetrahedral plasmas, the octahedral plasma, and the plasma frequencies and oscillation amplitude depend very strongly on the situation of load in the bore of the screen due to the S and the electrons. All right, so this is essentially the outline, the framework, which shall be used to try and rationalize and to bring to a rational understanding situation the wonderful phenomena which have been revealed in the last 4 years in the PDD system. So therefore, as I told you, I shall try to answer the questions which I posed, the two types, alpha and beta, within the quantum electrodynamics coherence condensed matter framework, and some of this are just some of these ideas have been dealt with in this paper, which has been published in the proceedings of the Rome workshop in February 1993. Now, the first question I would like to answer is why does the D2 in the gas go to the D in the lattice, and why does the P atom really split into independent dynamics in the lattice? Now, when you have a D2 in the gas, you have to see three steps. One, okay, kinetic step where the D2 goes to the surface of the layer. And this step is fully governed by the chemical potential of the D2 gas. This is a unit, so unfortunately, I'm a high-energy physicist, so I don't have to write down H bar C and the Boltzmann constant, so I put them equal to 1. Okay, and this is just an expression, rather than an expression for the chemical potential of the D2 molecule. So then the D2 is on the surface of the layer. However, just because I have the plasmas I told you about, like the palladium, the electron plasma, and the palladium plasma, okay, there are evanescent waves from this coherent electromagnetic field, which are associated with the coherent plasma, which of course just get out of the system at the surface, and the surface you have discontinuity. And you can solve the problem, the quantum mechanical problem, what happens to the molecule in such a field, and then you see that there's a very high probability that this system, in fact, becomes a highly localized system, like this, and therefore the D2 molecule gets into 2Ds and the 2 electrons, which are represented in this way just because the electrons are highly localized. Actually, this is just the kernel of a theory that, in fact, brings back the bibuccal to a scientific rationality, which has enjoyed. But of course, I would be happy to explain all my chemical friends why the bibuccal is not rational this time. Okay, the first step is just now we have a delocalized system on the surface. This is ready to go inside if the chemical potential inside is good enough. So the important point is that this dissociation step is now that the electrons and the neutrons enter the lattice in an independent way, and they have an independent dynamics, and this is very important. So now we are ready to understand the alpha phase, and therefore to answer the question why the D plus so mobile, the lattice IX, and what are the phases of the system. Now, if you do the calculation of what happens to the chemical potential of the electrons inside the lattice, okay, you calculate this curve. Notice, in fact, that the chemical potential becomes endothermal, you get energy at a rather low value of X. This is X. Whereas this chemical potential is just calculated for the D classes as a gas, which is just distributed in the octahedral position, and this is just a chemical potential coming from configuration of entropy, which is given by this form here. This is the alpha phase. Finally, this mysterious alpha phase just coming out, just because the chemical potential of the alpha phase, which is the sum of the chemical potential of the electrons, and the configurational entropy chemical potential of the deuterons in the octahedral position, is in equilibrium with the chemical potential of D2. Now, if the calculation is accurate enough, you will be able just to get from this the total description of a part of the phase diagram. The phase diagram which has to do with the equilibrium between the gamma phase within the gas phase and the alpha phase. However, this only happens, of course, for x less than 1. And this is very close to what is experimentally observed, quantitatively. Now, if you just jack the chemical potential of the D2 up by decreasing the temperature and or increasing the pressure, no, I'm sorry, it's the other way around. Okay? A new phase can be accessed where the D classes form an octahedral plasma. In other words, the alpha phase is no more in equilibrium with the gas, and now you calculate just on the basis of all this assumption about the alpha and the beta and the gamma phase. The beta has the deuterons in the tetrahedral, in the octahedral position, the gamma in the tetrahedral position. Now the chemical potential is again the sum, the beta phase and the gamma is the sum of the electron chemical potential and the chemical potential of the octahedral plus is the beta phase, but one can have instead of the tetrahedral plasma, tetrahedral plasma. And the interesting thing is that there is a crossover here. In other words, up to 0.5 and 6, the minimization of the chemical potential, is just in the beta phase, but then around 0.6, 0.7. Of course, this is not very precise. You have a crossover from one position, from one position to the other position, from one plasma to the other plasma. So therefore, we get to a new phase, the gamma phase. Now, the existence of the gamma phase was predicted just at the first annual conference in cold fusion. Of course, everybody was telling me they didn't know the facts, so I should go back to the basics. But on the basis simply that in the beta phase, you can't have cold fusion because the D's are too far away. The tetrahedral size can accommodate more than one, whereas the octahedral size can't. And in the tetrahedral size, which are closer to the D shells plasma, you can have some effective spring of the Coulomb repulsion. So all of, if you believe in cold fusion, you can't have cold fusion clearly, by having the D pluses in the octahedral position. Now, is there any evidence of this? Yes, I think so. And these are the data. Mainly, I just don't have this reference, but it's a very recent one, and I think Martin has a copy of this paper. So these are the data of Mengoli, and this is a good fit of this data. And then you see essentially that if you put the diffusion coefficient, in a linear scale, you can represent it this way, and there is certainly a discontinuity in this concept, where you have a very large diffusion coefficient, which goes all the way up to 10 to the minus 5 centimeters squared per second. And I recall here the diffusion coefficient is related to the Einstein mobility and the derivative of the chemical potential here, which of course shows that the very large derivative is refined. So good. So the I of 1, you see the I of this experiment. So if we fit the D's, the diffusion coefficient, the beta and the gamma phase in an appropriate way, we have based some analysis and we can get a good account of a set of very interesting experiments that were carried out at Imran, France, a Fleischmann, and I hope that Martin will talk about this. So I can conclude at this point that the gamma phase transition about 0.7 is really, in the loading equation, is really so we are now ready, I believe, to answer the last question. Alpha 5 and alpha 3, what happens during electrochemical loading in the Fleischmann pump cell, and why one observes heat after death. Now, let's try and understand what electrochemical loading means. It's a means to drive the system out of thermodynamic equilibrium, of course, but how? Because here you have a current of difference, which is just directed by the electric field of the electrolysis towards the cathode, the PD cathode. Now you have two Ds coming out the electron. Now this is taken. And then you have at least three avenues here. The D2Ds actually, they combine with the electrons that come the other way and they form a D2 molecule, and then this molecule will make bubbles and then escape. And this, of course, the probability of this formation depends on the diffusion coefficient of the surface. How well can the D plus travel on the surface? Or they just stay there and they sort of form a double layer. We will see this which will lead to surface chemical potentials. We'll tell you why they will form a double layer there. Or they just go in and they continue loading the system. Now, as I told you, in order for process 1 not to exhaust the D plus term, which is coming, it is necessary that the surface coefficient, the S, be something very slow. I mean, this is just an estimate in the terms of the current here. So, of course, and this tells you that you need to form some kind of map at the surface in order not to let this the D plus is diffused too rapidly and therefore combine rapidly. And here is really, the explicit, defined way, that our friends were able to implement, and therefore to be able to go to very high load. So really, from this point of view, it seems to me that electrolysis is a rather defined part, just because you want to do that. Now, if we're able to go to very low, to this very low surface diffusion coefficient, then in order for process 2 and 3 to work together, to really be able, so that they can, once you have something, you can really hold the system together, you need two strange phenomena to occur. One, you have to have the formation of, the emergence of a negative surface chemical potential, and related to this, you have to have a bulk electrochemical potential, which has arrived in terms of this chemical potential, which is due to this, the loading of the lattice, which at high loading becomes highly positive. So you have something highly negative that ought to compensate for this. Okay? Now, the crucial variables of this, besides the temperature, which we see one, are X, of course, and the current ratio, which is just the ratio between the surface density of the D pluses and the palladium surface. Now, it is absolutely miraculous that the picture quantum electrodynamics and condensed matter, in fact, can explain, indeed explains both phenomena in terms of ponderomotive forces, which are well known from laser physics. Again, the surface is the place where you have discontinuity in the evanescent way, you have in the electromagnetic field. So you have the possibility of having a ponderomotive potential, which is associated with the Lorentz vector, the Lorentz scalar, the Lorentz field square, and it's inversely proportional to the mass. So this ponderomotive force is mainly affecting the electrons and not the deuterium, because there's a ratio of 4,000 between the mass of the deuterium and almost the mass of the electron. Okay? Now, if you do the calculation, you notice very large electric field. However, it's also very interesting dependence on X, like X to the 3 amps. Now, due to the fact that the ponderomotive forces duty lines. Okay, and displace them by quantity Z bar, which you can calculate in terms of the work function, and it will be of this type. This is centimeter, of course, so this will be 2.24 angstrom times x to the 3 halves. You have this formation of the double layer, which leads now to a negative surface chemical potential of this form, which can be estimated to be minus 0.3 electron x cubed. Notice it's very large, depends on the loading ratio. And this also induces a positive electrochemical potential, of course, because, this double layer, you have an internal layer of D pluses, so when the D tries to escape from here, it will find a barrier from the D pluses, so it will just be let in. And therefore, this system essentially holds together, okay, which has this structure here, proportional, of course, to the Gaussian ratio, and then as it gives for this factor here, 5 electrons, the x squared, the x dependence. So I think that this, as far as I can see, is completely explaining the strange phenomena, and so therefore we can now use this deduction in the equilibrium condition for the electrolysis. Now, the electrolysis equation would also be that the surface potential would be the surface potential due to the undermounted forces and the time-dependent, very important term that comes from the configuration and entropy of the. It's like a two-dimensional Boson gas on the surface of the charges, and so therefore this will have certainly a free energy which depends on the temperature. There will be energy contribution. Notice negative, so it is the temperature will increase this term, and the bottom chemical potential will be the gamma chemical potential, which you can estimate for high loading from the diffusion coefficient. It would be like this, and then this, which is exactly that. So the equilibrium condition will be that the surface chemical potential will be equal to the palladium, the bottom potential, and this will fix lambda as a function of x, which is this. Now, if you're able to achieve the lambda with some protocol, then it will give you x, and x will give you the chemical potential here. So I will depend essentially on your ability. This is really all your smartness, your craftsmanship to achieve high lambda. And I don't have time. But then by looking at the condition outside of here, and also, the heat output, I think you can give a very good account of what Martins have observed in the electrode after the interaction with the electrolysis current. Fine. Okay, but I haven't said anything so far on cold fusion, and now I have to do that. Now, cold fusion. Well, I really don't have very much to present since all these papers that have been written, and so therefore, for people who are not familiar with them, let me remind essentially what the idea of this quantum electrodynamics on condensed matter is. Okay. Now, the first question is, how can one overcome the Coulomb barrier, which is a difficult problem? Of course, Peter is very smart. He doesn't want to answer this question, so therefore he shuttles humans around all the time. It's okay. I mean, nature, this is a part of nature, but there's another part of nature, and you have to take that into account. Okay, so let me go back to our phase-centered lattice. Okay, so here you have this plasma. Now, in the gamma phase, you have the neutrino, which I have this black region around here, the gamma phase, and then a very large negative potential, which oscillate back and forth. But the point is, when this gets here, then you have this, and then when this gets back here, you get the other side. So this region is always filled with this very highly concentrated and high mass, because the D band is very narrow. And this naturally resulted only to a very long wavelength. In a coherent situation, this is also to a short wavelength. And this is just what I have described, and Martin has described, the failure of asymptotic. And so just not to have again, the people say, but don't you know? Yes, I know. And you are wrong, because this is predicated on the fact that you have the electromagnetic field is Coulomb on one side, but Maxwell on the other. Why do we have to throw away Maxwell and take Coulomb? Or vice versa. So, and the concentration of charge is realized that the electron plasma generates a screening potential as a function of size, the direction sideways, and how. These are the famous or the infamous or whatever, maybe nobody knows about them, deep holes at the tetrahedral side. This creates another potential which has actually surpasses the Coulomb potential. This will calculate the gamma amplitude. But this is rather large at the bottom, 85 electron volts, which is perfectly compatible with also the plasma frequency in terms of energy. So the typical brain, Leggett and Kuhn, all these people, high power theorists, are calculators which are usually quoted by these people who want to take the Surgeon General advice, warning, so they get 10 to the minus 51, and then you get a 10 to the. So you increase this by 27, 28 orders of magnitude, the square of this. So Coulomb spinning is well understood, leads to Jones type, referring to the Nature paper 89 rates, which of course are about 10 orders of magnitude lower than required by flash composites and speed. Indeed, if we think that this is all that happens, we do get fusions of the type some fusion percent of the centimeter cube of collision. So the other question is, what is the new fusion dynamics? Of course, if Fleischmann and Pons and Mars and helium-4, blah, 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 and Gozzi, G, and so on, so right. So therefore, there must be some dynamics, okay? And so this cannot be equal, and cannot be the leading one. So what is the other thing? Okay. Now, let me recall that the D classes, the fact the D in the 3D lattice are a strong electromagnetic coherence field which is generated by all the plasmas that are around. I take one, the strongest of this is the one which is created by the oscillation of the palladium, the PD nuclei. And now, in such a field, suppose now that you have a limit excess which has come close, goes with an amplitude of close the gamma amplitude to the plasma D which sits on the tetrahedral sides. Okay? Then quantum mechanics, if the system has a current, a nuclear current, then the Hamiltonian interaction is of this type here, then the system will just make a transition from this one to all the states which are there at atomic number 4 in charge 2. Diagrammatically, the interaction is this one. We have this, we have the current operating, the nuclear state, and so the nuclear state. Now, what is the nuclear state? Well, the nuclear state is there will be some kind of scheme like this. You start with the DD, okay, and then this can go to P state, and the helium-4 that there is here, another helium-4 excited. This is the trigger state, the state that was emphasized at the beginning. So, okay, so this will be, this is the Schrödinger equation. We just use this position. I mean, very fast notation on the state. This is, of course, only a very simplified system state. But just to say that you can go from DD to helium without violating parity. So you solve this simple problem of three-state evolution. So the nuclear state is a combination of the states, and you can calculate the solve the Schrödinger equation, this Bayes coefficient, and you compute in this way the transition amplitude over time, T2 pi over omega r, which is the time in which the excess, in which the electromagnetic field, which is a part of this dynamics, the coherent electromagnetic field, relaxes its energy to the lattice in various forms, mainly form excitation and therefore excitation of heat. Okay? And from this, which is just quantum mechanics, notice here, however, to the fact that you have a plasma state, that this angle is proportional to the number of units that have a coherence domain, MCD. The coherence domain is essentially the domain which is within one wavelength of the electromagnetic electric field, which is associated with this coherent process. Because this is the minimum unit where you can have coherence. So I'm taking here the realistic, low pessimistic, that assumption that in fact you have no coherence extending beyond the coherence. Actually, just to focus the problem at zero temperature, you know the Nash theorem requires that the coherence domain in fact encompasses the whole